Okay, hello. Welcome back to AMT 180 Aircraft Instrumentation. I am going to go ahead and get started. Please type in the chat if you can hear me. Let me know that you can hear me and that there's no problems with the audio. I'm going to get started today. Lecture's probably going to be... Okay, thank you, Ken. I see. Let me expand this. Lecture is probably going to be a little shorter than usual today. We're just going to go over the last of the pedostatic system. It should be a review for most of us. I think the majority, if not everybody in the class, has had a chance to get on the pedostatic system project. In last week, I had some trouble with my audio. So there were some videos for lecture that if you watched were pretty informative. I know that we left off kind of with troubleshooting the pedostatic system. So I'm just going to do a little bit of a review, and then we're going to talk about the primary flight instruments today. We'll cover a lot of information about the altimeter, vertical speed indicator, and turn indicators before getting into gyroscopic instruments and how those work in the next lecture. So the pedostatic system, what's the function? It's to gather and distribute various air pressures for flight instrumentation. There's someone listening to lecture outside of the door, and I can hear whoever that is. So I can hear myself. Pedostatic pressure sensing flight instruments. So we have the altimeter. That's not supposed to be plural. Oops. We have the altimeter and altitude reading, which our altimeter is our altitude reading. We have our vertical speed indicator and our airspeed indicator. And these instruments are all pressure-sensitive instruments. They are monitoring a pressure in order to deliver the information. The pedostatic system is a combined system that utilizes the static air pressure and the dynamic pressure due to the motion of the aircraft through the air. These combined pressures are utilized for the operation of the airspeed indicator, altimeter, and vertical speed indicator. So in our pedostatic system, we have our static pressure or ambient pressure, which is always present whether an aircraft is moving or at rest. We have our dynamic pressure is present only when an aircraft is in motion. Our ASI, our airspeed indicator, is the only instrument that utilizes the pedo tube. Our altimeter and VSI utilize only the static pressure that is derived from the static port. So airspeed indicator connected to our pedo system, altimeter and vertical speed indicator connected to our static system. These are some of the instruments and associated instruments that make up the pedostatic system. So we have pedo tubes and static vents. In a digital reading system, we can also have our air data computers, or also called ADC. Also digital air data computers, or DADC. Pedostatic pressure sensing flight instruments, which again are our altimeter, vertical speed indicator, and our airspeed indicator. We also have our pedo tube, air pressure ports, tubing, and instruments. So those are just some Things to keep in mind when being asked what makes up the pitot-static system. I believe this picture is out of the 8083 handbook. So this is just a simple diagram of your simple pitot-static system. You have your pressure sensing instruments, you have your static line, your pitot line, and an image of a pitot-static tube. This would be your static port, all in connection with your instruments. Here we have your altimeter and we have your speed indicators. So that is kind of a block diagram of what your pitot-static system consists of and what it looks like, how they're all connected. This is also a diagram out of your 8083 handbook. It's basically a schematic of how a pitot-static system is connected in an aircraft. This is also a little bit more of a complicated system, not like the image before that was a very simple, basic system. Here you might have an example of a more complex system, such as in larger aircraft, possibly aircraft with more than one engine. So that's a good schematic to look at. You have your pilot's instrument pitot tube up here, co-pilot's instrument pitot tube, static vents and drain valves in the nose gear well. So that's an example of something that would be, this would be a diagram for a larger type aircraft. And it's just mimicking what's on one side is going to be on the other if you have a co-piloted aircraft. We have flush-mounted heated static tubes on both sides, and we want those to be heated to prevent ice accumulation. We have equalizer manifolds on your pilot and co-pilot sides. Some more flush-mounted static tubes. Sumps and drains. Autopilot static drain valve. You also have pilot's flight instrument panel labeled over here. So this would be the nose, the forward of your aircraft and working back. This is where the pilot and the co-pilot would be, and where those associated items would be in relation to those spots. Talks about your autopilot amplifier, which we'll get into at the very end of the semester, the autopilot, just a little bit, because we do cover autopilot in the navigations and communications class. You have your selector valves, cabin pressure control panel, static drain tee, and then this is also telling you which lines are your static system and which are your pitot pressure system. You also have a good diagram of your instruments here, so it lists them for your pilot and co-pilot. So definitely a diagram to look at before you do the pitot-static checkout. Primary flight instruments. So, like we've been covering, our pitot-static system and instruments, these are considered some of our primary flight instruments. And remember, those three instruments in the pitot-static system are our altimeter, our ASI, airspeed indicator, and VSI, vertical speed indicator. We also have gyroscopic instruments, which will be our turn and slip indicators and our turn coordinators. Primary flight instruments provide the pilot with data about the flight situation, such as altitude, airspeed, vertical speed, heading, etc. So we covered this in the very beginning of the semester, our 6 primary flight instruments. We have our pitot-static system, which is our altimeter, which is connected to our pitot system, our ASI airspeed indicator, and our VSI vertical speed indicator. Our turn indicator, attitude indicator, and heading indicator are all operated gyroscopically. And those make up our 6 essential flight instruments, primary flight instruments. So moving into talking about our altimeter, the pressure altimeter is an aneroid barometer that measures the pressure of the atmosphere at the level where the altimeter is located and presents an altitude indication in feet. Remember back to the beginning of the semester when we talked about aneroids and baffles and diaphragms. So that is the device that operates within your instrument to give you a reading. An altimeter is a stack of sealed aneroid wafers evacuated to an internal pressure of 29.92 inches of mercury. So the wafers that are within this aneroid are free to expand and contract with changes to the static pressure. If we have wafer compression, then we will see a decrease in altitude if operating correctly. Wafer expansion will make an increase in altitude in your instrument. The expansion and contraction of the wafers moves the mechanical linkage which drives the needles on the face of the altimeter. The altimeter is an instrument that measures the height of an aircraft above a given pressure level. So that's what we're looking for in the altimeter. It's going to measure the altitude above, let's say, 29.92 on a standard day, what is deemed a standard day. The altimeter uses static pressure as its source of operation. Air is denser at sea level than at higher levels. And as altitude increases, atmospheric pressure decreases. So some simple science there. And those are the laws that the altimeter works off of. This difference in pressure at various levels causes the altimeter to indicate changes in altitude. Adjustments for non-standard pressures are accomplished by setting the corrected pressure into a barometric scale located on the face of the altimeter. This is called the Colesman window. If you don't know what I mean by the Colesman window, there are pictures in your textbook. You are definitely going to want to know what that means. If you've done the pedostatic project, you've probably seen the Colesman window, which is where we read what the barometric pressure is set to. I don't know I had a picture on here of an altimeter, but you guys can just as easily look that up as well. So make sure you know what the Colesman window is. And just a note there, cold air is denser than warm air. Airspeed indicator, our ASI, it utilizes both the pitot as well as the static system. ASI introduces the static pressure into the airspeed case, while the pitot pressure, which is dynamic, is introduced into the diaphragm. The dynamic pressure expands or contracts one side of the diaphragm, which is attached to an indicating system. The system drives the mechanical linkage and the airspeed needle. I believe at some point we also watched a little video on this. Might have been when we were going over the operating devices within the instrument, but there was a good video showing how this works. The expansion of one side of the diaphragm and the moving of the mechanical linkage. Markings for our airspeed indicator. So the markings go like this. We have green, which is our operating range. We have yellow, which is our caution range, and we have red, which is our never exceed speed. Similar to many of our other instruments, it's a pretty standard system, green, yellow, and red. When the aircraft is utilizing that color code system, you'll see a lot of the same colors on your instruments. Our vertical speed indicator, the rate of climb or descent is indicated in feet per minute, FPM. A VSI indicates whether the aircraft is climbing, descending, or in level flight. VSI operates solely from static pressure. It is a differential pressure instrument. Inside of the diaphragm is connected directly to the static line of the pedostatic system. The area outside the diaphragm is also connected to the static line, but through a restricted orifice that is considered a calibrated leak. The diaphragm in our VSI receives unrestricted air. The case receives a static pressure via the metered leak. The differential pressure that is indicated on the instrument needle as a climber or descent. Different. Okay, so that's our VSI. Again, measures the rate of climb or descent, measures in 100 feet per minute, 100 foot per minute increments. Our turn indicators. There are two types of turn indicators. We have turn and slip indicators, which is a rate of turn in degrees per second. And we also have turn coordinators. These can indicate roll rate and rate of turn. Our turn indicator is the only electrical operated instrument in the essential 6 instruments in the primary flight instruments. This is only if you have all analog instruments. Of course, if you have a glass cockpit, then all of your instruments are going to be electrically operated. But every aircraft always has a redundant system, and at minimum will have an airspeed indicator, vertical speed indicator, and an altimeter that is in analog form for that redundant system, just in case we have some type of electrical failure. Turn indicators display the wing level. There's a left and right hand marking that indicates 15 degrees of bank, which is a standard rate of turn. Your turn indicators also have a 2-minute indicator, so if you've been in a turn for more than 2 minutes, your instrument will have an indicator, and it will usually send you a loud tone saying that you've been in that turn for too long. And these turn indicators, you'll see that they have a black ball indicator. It's a little long oval strip filled with liquid, and this black ball indicator in the center indicates coordinated flight or slip and skid. So when that indicator is in the center, it indicates that you are in coordinated flight. Turn and slip indicator. The gyro in the turn and slip indicator rotates in the vertical plane corresponding to the aircraft's longitudinal axis. Okay, so those are a lot of big words there, I know, but that's a very important part to understand about the turn and slip indicator and how it operates. And we will be getting into gyroscopic instruments, just the operation of gyros and how the principles of how they operate. We'll be doing that on Thursday. So for now, just keep in mind that the gyro in the turn and slip indicator rotates the vertical plane corresponding to the aircraft's longitudinal axis. Because of precession, a yawing force causes the gyro to tilt left or right, as viewed from the pilot seat. The turn and slip indicator uses a pointer called the turn needle to show the direction and rate of turn. Okay, so that's all that we're going to go over for today, just some of our primary flight instruments, a little bit of covering up a review of the pitot-static system, and we talked about our vertical speed indicator, our airspeed indicator, and our altimeter. Does anyone want to, if you would like to view any of these slides, I know there was a lot of written information, so I don't know if I went too fast for you guys, but if you'd like to view any of these slides, go ahead and type in the chat, and I can go through them. Other than that, that's it for lecture today. Don't forget to take the quiz. Don't forget to take the quiz by midnight tonight. And if you need this information for the quiz, don't forget that you need to reference your textbook. Trin, I see that you typed in here that you need the PowerPoint. What PowerPoint do you need? Because I can't give you the whole PowerPoint. You'll have to just go back and watch the lecture. Okay, so go ahead and type any questions in the chat. I'm going to turn my volume off, but I will be on the computer if you guys need to view any more of the slides. I know I might have went through that kind of fast. Other than that, I'll see you guys in lab in a little bit.